Humanity has always wondered how the universe began, but for almost its entire history, it lacked the scientific tools to answer this question. Things only changed at the beginning of the 20th century, when Einstein formulated the theory of general relativity. From the start, he tried to apply his theory to describe the entire universe, but in doing so, he encountered what he later called his greatest mistake. But what was this mistake, and more importantly, was it really a mistake? Let's try to understand. In 1917, just 2 years after completing his theory of general relativity, Einstein published an article in the Journal of the Prussian Academy of Sciences titled Cosmological Considerations on the General Theory of Relativity. It was the first time anyone had the opportunity to coherently describe the overall physical structure of the universe. The theory of relativity allowed the problem to be addressed by linking the distribution of all existing matter and energy to the geometric structure of space-time. At this point, it's important to recall the state of scientific knowledge about the universe at that time. For the previous 2 centuries, the only tool available to those who tried to understand and mathematically describe the universe had been Newton's theory of gravitation. Newton's theory had introduced a radical change in the conception of the cosmos. The motion of any mass in the universe, without exceptions, could be explained through the action of a simple universal law. For Newton, space was a rigid framework completely independent of the distribution of matter within it. Not only that, Newton believed that space extended infinitely in every direction and was eternal in duration. Celestial bodies could move freely through empty space, guided only by gravity, and therefore by the influence of all other masses present in the cosmos. Now, why did the stars appear motionless relative to each other and seem to occupy fixed positions in the sky? Newton concluded that they must be infinite and uniformly distributed throughout space. For if this were not the case and all the matter in the cosmos were distributed within a finite volume, its own gravitational attraction would cause it to collapse towards a central point. Instead, a uniform and unlimited distribution of stars could remain balanced. Thus, for Newtonian physics, the most likely scenario was that the universe was infinite and contained an infinite number of stars. This model also had another advantage. After Copernicus, humanity knew that Earth could not be at the center of the universe, and if the universe were infinite and stars were uniformly distributed everywhere, no one could claim to be at the center of the universe because there simply was no center. There was no privileged point in the universe. However, Newton's cosmological model was problematic in other ways. An infinite distribution of stars led to contradictory conclusions. For example, if there were infinite stars, the night sky could not be dark. It would have to shine like the surface of the sun, a problem known as Olber's paradox. Furthermore, Newton's imagined equilibrium was extremely precarious. The stars, in Newton's own words, were like years that were held in balance. Any small perturbation would alter this balance and lead to matter concentrating in some regions of space, leaving others completely empty. Such a universe could not have existed eternally. These difficulties were impossible to resolve through Newtonian gravitation theory, and when Einstein found his new theory of gravity, one of the first things he tried was to apply it to describe the entire universe to see if it could solve the problems left open by Newton. Einstein soon concluded that the universe must have a shape similar to the surface of a sphere. Of course, while a sphere has only 2 dimensions, real space has 3 dimensions, so this is more complicated to visualize. But the important point was that Einstein's universe contained a finite amount of matter, and, just like the surface of a sphere, it could be traversed in every direction without ever encountering a boundary. At the same time, space would have a finite extent. Traveling long enough would bring you back to the starting point. In short, general relativity allowed for a natural elimination of the infinite distribution of stars in the universe. According to Einstein, all the matter present in the universe curves space and gives it a closed and finite shape. Just as there is no central point on the surface of a sphere, so in Einstein's universe there is no center. However, there was a problem. At the beginning of the 20th century, astronomers still thought that the universe was eternal and that stars occupied relatively stable positions. Just like in Newton's universe, in Einstein's universe, gravity had to find a way to keep things unchanged and immutable forever. However, for Einstein, obtaining a static solution proved anything but straightforward. Even in Einstein's universe, as in Newton's, gravity caused stars to become unbalanced, collapsing on themselves or dispersing into space. To overcome the problem of the lack of stability in the universe, Einstein was forced to modify his equations, introducing a sort of tension into the structure of spacetime, a kind of negative elasticity, a repulsion that countered the tendency of matter to collapse. In this way, Einstein finally found a static solution to his equations and thought he had resolved the issue. But the price to pay was the introduction of a new quantity, called the cosmological term or cosmological constant, which had no other physical motivation than to stabilize the universe. The cosmological constant introduced by Einstein was not forbidden by general relativity, and in any case, it did not produce any observable physical effect as long as one remained within distances accessible in the laboratory or within the solar system. Its effect was relevant only on scales of distance comparable to the entire universe, and with this mathematical trick, Einstein had finally managed to construct a self-contained, eternal universe with a finite spatial extent, just as every physicist and astronomer of the time would have hoped. Max Born, one of the fathers of quantum mechanics, was literally thrilled with this model of the universe and said, "A finite but unbounded space is one of the grandest ideas about the nature of the world ever conceived. It solves the mysterious problem of why the star system is not dispersed, as it would be if the universe were infinite." In short, in 1917, Einstein's success seemed total, but in reality, things were a bit more complicated. Immediately after the publication of Einstein's work, increasingly accurate measurements of the velocity of what were still called nebulae at the time began to accumulate. But in 1924, they would be definitively identified by astronomer Edwin Hubble as galaxies external to our Milky Way. Astronomer Vesto Melvin Slipher had noticed that almost all observed galaxies seemed to be moving away from us. When mathematician Hermann Weyl pointed this out to him, Einstein seemed struck. "If the universe is not static," he replied in a letter in 1923, "then to hell with the cosmological term." Meanwhile, solutions to general relativity began to emerge that described non-static universe models. Between 1922 and 1924, Russian mathematician Alexander Friedmann showed that if the universe contained a homogeneous distribution of matter, without a cosmological constant, space would have to expand or contract. In 1927, physicist and priest Georges Lemaitre found similar results and showed that the universe could expand even in the presence of a cosmological constant. Around 1929, observations by Edwin Hubble and Milton L. Humason definitively showed that there was a clear tendency for galaxies to move away from us, with speeds that increased proportionally with their distance. If one did not want to hypothesize being at the center of a strange universal flight, the only sensible interpretation of this data was that space itself was expanding. But Friedmann's and Lemaitre's works were long ignored, particularly by Einstein, who was at least cool towards expanding universe models. He thought Friedmann's work was simply wrong, and even wrote to complain to the journal that published it. Later, he admitted that the model was mathematically correct, but was not convinced of its physical validity. He had an equally low opinion of Lemaitre's model. It is said that during the 1927 Solvay conference, Einstein judged the physical sense of Lemaitre's model to be abominable. However, the truth was that Lemaitre's and Friedman's models perfectly matched Slipher's and Hubble's data on galaxy speeds. The final blow to Einstein's static model came in 1930. Arthur Eddington, who had helped cement the triumph of general relativity by observing the deflection of light predicted by Einstein in 1919, demonstrated that the model with a cosmological constant was indeed static, but also highly unstable. In practice, Einstein's universe was like a pencil balanced on its tip. A small perturbation was enough to make it fall dramatically towards expansion or contraction. Gradually, Einstein was forced by the evidence to abandon the idea of a static universe and, albeit reluctantly, he converted to the new cosmology in which space was expanding and the universe originated from a defined moment in the past, the Big Bang. Thus, it seemed that there was no need for the cosmological constant. The first to regret having introduced it was Einstein himself. In his 1945 book, The Meaning of Relativity, Einstein wrote that the introduction of the cosmological term in the equations of gravity, although possible from the point of view of relativity, should be rejected on the basis of logical simplicity. If Hubble's law of expansion had been known at the time of the creation of the general theory of relativity, the cosmological term would never have been introduced. Today, it seems even less justifiable to introduce such a term in the field equations, as its only original justification, namely providing a natural solution to the cosmological problem, has vanished. In 1947, he wrote to Georges Lemaitre, "Since I introduced this term, I have always had a guilty conscience. I cannot believe that such an ugly thing actually occurs in nature." Bernier, the physicist Sagan recounts in his autobiography that one day Einstein, now elderly, confessed to him that introducing the cosmological constant into the beautiful equations of general relativity was the greatest blunder of his life. Today, we know that the Big Bang model best describes all the observations we have. Indeed, it predicted the expansion of the universe and the creation of the model we now consider correct, even though it was the equations of general relativity that allowed us to arrive many decades later at the right answer. But the even more ironic thing is that what Einstein considered his greatest mistake, namely the introduction of the cosmological constant, was not actually a mistake at all. In 1998, two groups of astronomers, led by Saul Perlmutter, Brian Schmidt, and Adam Rees, discovered that the expansion of the universe is accelerating and were awarded the Nobel Prize in Physics for this. In 2011, the most likely explanation for the acceleration of the universe is indeed the cosmological constant. If the universe is expanding, the repulsive term introduced by Einstein to make it static actually causes it to expand even more rapidly. In short, jokingly, we could say that Einstein was right even when he thought he was wrong. But in reality, this story shows us that science is not made up of infallible geniuses, but is a much more complex and, above all, collective process. Sometimes a wrong path is taken, but what matters is the overall journey, and in the end, even mistakes can provide useful lessons. If you enjoyed this video, please leave a supportive like and subscribe to the channel.